Hello, I'm Valerian Lalucaa from the CNES. I will present you the image sensor for space applications. First, I will introduce quickly our team. We are the optoelectronic detection team because we look at the sensor and all the electronic analog and part of the digital detection chain. We cover a very large portion of the spectra, since we have people working for X and gamma rays detection. We also have people in UV. We also have people in visible, of course, and infrared from short wavelength to long wavelength. So it's a very large and broad detection field, and also diverse specificities, technical specificities. Today I will talk mainly about visible image sensors. For the image sensors, we are looking at a very broad range of applications. First, of course, historically, the CNES has done a lot of Earth observation, and as we know today, it's very useful field. And also for the science, a lot of astronomy. But more recently, a lot of fields are started to come up, starting with the attitude control, so that the spacecraft can know where it is. And of course, the engineering, when we talk about image sensor, and the rover need awareness of its situation, and the cameras are there for that. And also communication. So we have recently see an interest in the communication with pixelated array. So first I will give a small reminder of what an image sensor is. So you have photon incoming from a source and from a scene, and they are focused by the optics. And the image sensor role is to actually convert the light, the photon, to electrons, meaning an electric signal that you can get out and use into electronic system like the onboard computer. So basically what you want is having some linear relationship between the sensor and the electric signal you get out. So here is an example of what we get, and in practice, of course, the pixel response is just not a linear curve from 0 to how much photon you want, but have some performance related to a linear part and an offset part due to dark current and the sensor itself, and eventually a saturation where the sensor cannot know the incoming flux. For the image sensor, you need quite a large development scheme. If you want to do an image sensor, you need first a specification list, and then you can go to design, where the design house or the design team will have to see how much implant and where the implant will be, so you can have a mask out of this design house. And then you go to a foundry, where people will actually make implant inside the silicon, so that you can have you can form the pixels and the photosensitive element and the transistor. In imaging, we also have a post-process, meaning that we have extra steps, including, for example, a thinned wafer, so that we can have a nice optical performance. And then you go to what we call the back end, where you actually need to look at the wafer, the silicon disk, and see which die is working and which is defective, so that you can use the good dies and put them into a package, usually a ceramic package with the window. And then you can go to characterization to make sure that all the performances are as expected. That's not all, because once you have packaged devices, you still need to make sure they are working as you wanted to design them. And in space, we have quite radiative environment. So we have galactic cosmic ray, quite energetic particles, and at the same time we have solar particles, so a lot of protons, and also van Allen belts with trapped protons and electrons. So you need to test for all of that, and that's the two pictures on the right, where what you have in space you want to replicate on your sensor using, for example, a particle accelerator facility here, protons. You also need to test for the vacuum environment and the large temperature range you might have into a specific project. So once you've fabricated the sensor, you still need to qualify it on all these harsh environments. So the qualification is done on a series of tests, and what we do usually is have a screening, for example, so a choice of the component to make sure that there is no youth defects. Then we go to the lot acceptance test. Basically, we take a few components and we test them into very harsh tests like thermal cycling or mechanical shock, and we make sure that after analysis and after destructive physical analysis, we still get the nice part out. And you need that for every image sensors. When you talk about image sensors, you have two types of image sensor. The first flown into space was, of course, like on ground, the charge-coupled devices. Basically, these are small gates above the silicon where you control the electric field. And with that, you form potential well that you can shift from under one gate to the other ones. So that the small animation you had on the side, and if you do cross section, you see what it is. Actually, that's kind of polysilicon or metal gates on top of an active silicon with a small sheet of oxide. And that is very interesting because as you can shift the charges, so the electrons of the photo generated in the silicon, you can actually do that in synchronization with the image. So basically, when we talk about a satellite, we have a mode of operation called push broom, or also TDI, time delay integration, where the satellite's movement will make the image move on the sensor, and we synchronize the charge transfer to the movement of the image under. So it's basically a scanner that we had before in the old days, I would say, where you use the satellite movement as a scanning movement. So CCDs were very high and are still very nice components to do that. And in the frame of the CNES and also in Airbus, we had the Spot family, Spot 1, 2, 3 in 1990s, around 1990s, Spot 4, 5, where we increased the resolution and down to Pleiad. And then Airbus did Spot 6, 7 and Pleiad Neo. And you can see some frame out here. So what is inside is actually what I just told you about. Basically, it's just a linear format CCD. Here in the frame of the Pleiad project, it was 20 times 6,000 pixels. So you had 6,000 pixel wide image out, and you have a pitch of 13 microns. So already the pixels are quite small. And these kind of CCDs were all used in diversity of projects outside the CNES, and most of them also use the array format. So basically an array of pixel, and you can find them in all kind of projects, like a lot of science with Gaia, Korot, Plato, and Euclid. For example, in Euclid, what was used here is taking the nice very small gaps between components so that you can make a very, very large array of components without losing too much space between them. But on the ground, people started to look at this new technology, what is this CMOS, complementary metal oxide semiconductor. So people were trying to do imagers using the CMOS technology. CMOS technology is an electronic technology using metal oxide semiconductor, and it's complementary because you use PMOS and NMOS transistor alongside, and that is very interesting for the power. You have very nice, very low power consumption. And you can also, since it's a technology for this transistor, you can also have photosensitive element and CMOS circuit on the same device, and people were trying to do that with a active pixel sensor, where you can actually address every pixel independently and read them in succession. And basically, you see on the right what it is doing. It's basically transistor and a photosite element here. And doing so in let's say, electronic technology is interesting, but you can get the most of it using custom imaging steps that people developed over the year on ground, let's say, using pin photodiode for the performance of the photosites. They started sharing transistor in order to get more, to lose less space for the transistor. They started to isolate the pixels so that you don't have crosstalk between optical and electrical crosstalk between pixels. They also focused the light in the photosite using micro lenses. They started to use color filters to have color imagers, and subsequent improvement using backside illumination and 3D stacking to have the transistor below the photosites. And that's why here you can get to a quite advanced device today on the ground. Historically, the first application to use active pixel sensor were actually star trackers. They were very interested at the fact that you can actually address a subportion of the pixel very easily, and that you could do some addressing. And they started to use that to map, of course, the stars in order to know where the satellite is. Historically, that was done in the HAS2 array with the Hydra star tracker, and then the 3D plus cube inside the Auriga star tracker, using commercial off-the-shelf components. Then people started to see the interests for the more conservative mission with science and engineering, and they started to do all of this, to use these CMOS active pixel sensors inside all kind of mission, including the Sentinel-2 here. For example, we had GOSI 1 and 2, Light Imager, and FSI with MTG. What happened just after that was the rise and the use of these commercial off-the-shelf component to do some very nice cameras and very compact cameras, and that was very interesting, especially for the small craft and for the rovers, obviously. So the Mars 2020 was a nice example, because on this Mars 2020 rover and alongside vehicles, I would say, there was more than there were about 23 cameras, and mainly CMOS image sensors. So here are a few of them for the Perseverance rover, where they had HazCam, hazard cameras, navigation cameras and also the lander camera here. And for, let's say, our participation, it was the co-development with 3D Plus to have this Caspex, what we call Caspex cube, and that Julien presented earlier. And we had that inside the mass cam here in order to do very precise images using the same optics than the laser shooting spectroscopy instrument. So here are a few example of the images that the NASA could get out. And you see, for example, the context with the navigation and the documentation cameras. And here are a few images of the what we call the RMI, remote micro imager, with a 3D Plus and CNES cube. And people started to see that this instrument is very resolute. This is 2 centimeters, and that was very useful because for the scientists, they started to do a lot of picture in order to find out and assemble a very large picture with a lot of resolution. And actually what they did, and you have here an extract of the publication, is having a very nice analysis of the small Kodiak. They call this small mountain Kodiak, and they could extract a lot of information that which were very interesting to find the history of the site. And here you have a small view of what they could, let's say, project from the conclusion of the crater about 3 billion years ago. And we are still continuing this kind of development with small micro cameras. For example, here we have the MMX rover project, where which is going on the Phobos, the Mars moon. And there we have a few cameras. We have 2 navcam, so that actually we have a very large field of view, about 83 degrees for the edge. And 2 of them so that we can extract stereo information so that we can know the depth on the site. And of course, that will be mainly engineering cameras, and the scientist wanted also a camera. So we had also 2 what we call wheel cam in order to look at the wheels that you see here. And these wheel cams are very narrow fields so that you can have more, also more resolution on the sites. In the future, we have a lot of mission going on, and I would say that the big ones, of course, like military, are still using custom sensor and CCD-like technologies. And increasingly, people are turning to commercial off the shelf. For example, here we have Co3D, which is aiming at doing with a few satellites 3D imaging of the ground, so that we can have 3D maps, 3D model of the terrain using imagers. For the micro camera, we had, of course, Rashid issue recently with Rashid 1. But we are looking to do the Rashid what we call extended, so that we can mainly use the Rashid 1 design to do a small mission. So it's going to the moon. And then we are continuing this good collaboration with the Emirates using the Rashid 2, where I think Julien also told you that we are going to have multispectral at the pixel level, multispectral filters that can actually be used to have a look at a very narrow band of the wavelength. And that will be very useful for, especially for the scientists. Here is an example of the moon seen in a multispectral way, and they can extract a lot of geological information on the minerals with this kind of cameras. In conclusion, I will say it's difficult to conclude, but we had lots of history in the CNES, especially with custom build sensor, and now the attractive performance and cost of the COTS make it very interesting. You will still need qualification either way, and especially with the COTS, you don't know will it work or not. And today, only the really big players, big companies, or actually states can actually pay for custom sensors, and that is pushing, let's say, the demand for the COTS sensors and the need for this kind of development. And it also explained the success for the let's say co-development of the off-the-shelf space qualified camera. Of course, this is still going on, and we are looking at a lot of things, not only increasing resolution, but also going for an extension into the infrared, but also into different bands, different type like polarized filters or multispectral bands. I thank you for your attention, and now if you have question, you can still ask in the chat. Okay, so I think there is one question, and what are the future advances on CMOS technology for space cameras we can expect? That's a question that a lot of people are wondering. In the framework on the ground development, what people are pushing is actually the integration of all the electronics in the same chip as we do in the same chip where we have the pixel and the light detection. And this means that you will see increasing devices with stacked silicon, stacked lattice of silicon layers, where we'll have the photo detection on the top level, and then you get a lot of transistor on the bottom layers, so that you can add increasing function and smart function inside the same chip. And that will be the development that will happen here on the ground. And that is still a question here, because for the radiation hardness in space, it's not sure it will hold much. So I think what on ground and also in the space, we will have this push for more integrated let's say a smart function on the device. So maybe at some advanced future, maybe even the FPGA or image processing directly on the same chip. Are you getting support from COTS manufacturers of image sensors to support the qualification for space use? That's a tricky question. I will say yes and no. Some of them are giving support and some are not. And the question is about their willingness to address the space markets. Some of them are interested because they are interested at having space imagers for a lot of customers, and they will ask us to help, and maybe we can help them. But some are actually doing imagers in very large quantities for all the ground application. They won't talk to us because we are just basically a few pieces a year where they expect a customer to have millions, thousands, or at least. So in that regard, the space market is too small, and sometimes they won't help us. What about future expansion to the middle and long wave infrared range? Well, for the COTS devices, it's very interesting because the silicon is a very mature material, and that means that we have very, very nice performances. When you go to middle wave and long wave long waves, you need to change the detection material to have a cutoff wavelength that is, let's say, higher. And that means you have like indium gallium arsenide, or maybe some MCT, mercury telluride, telluride cadmium. And then these are not really let's say, off-the-shelf component that you can get everywhere, and even the industrial that are making them are in difficulty to have a very controlled material. So these are not yet really COTS devices, and there is a lot of work to do. And I think it may happen with a different material like quantum dots, or that can actually have less performance, but maybe a lot cheaper, and maybe this can be integrated onto silicon readout circuit and then go into a camera. And that was my last question. I think that's it. So there will be a close-up session by the organizer now. And thank you for listening, and thank you for the question, and see you soon.